Okay, hello, my name is Aisha Fatima with ID number uh, 36, and now I want to tell you about process management in operating system. So, welcome to the world of operating system and the fantastic realm of process management. In this course, we embark a journey to explore the entire mechanism that govern how processes are managed within an operating system environment. From understanding the fundamentals of process of delving into advanced scheduling algorithm, this course offers a comprehensive overview of process management in operating system. Operating systems serve a backbone of modern computing, guessing the allocation of system resource and ensuring the seamless execution of tasks. At the heart of this functionally lies process management, which involves a creation, scheduling, a coordination of process to optimize system performance and responsiveness. Through this course, we delve into a core concept of process management, starting with an exploration of process states transition. We examine how processes are created, scheduled, terminate, shedding light into an integrated dance of CPU, schedulers, and scheduling algorithms. Furthermore, we delve into a realm of interprocess communication or IPC, exploring how exploring like how processes communicate and share data within an operation system environment. From shared memory to message passing, we uncover the mechanism that facilitate seamless collaboration within a process. Moreover, we delve into advanced multitasking and context switching, unraveling how modern operating systems enable current execution of multiple processes while entering for resource allocation and system responsive. So, whether you are building computer scientist, a software developer, or simply intrigued by inner working of operation system, this course offers a rich exploration of process management that will deepen your understanding of the computing fundamentals and empower you to navigate the complexity of modern computing environment. Okay, before we get started to study, we should know about what kind of chapter that we will learn about. We will separate into a 12 chapter. The first is about process state, process scheduling, process control block, schedulers, types of schedulers, CPU bound versus input, and CPU scheduling. And next about process termination, process creation, context switching, the process communication, producer and consumer problem in operating system, and the last is about inter-process communication. Okay, so first thing first, what is process? Like we will talk about process, but before we get started, what is process first? So process is the instance of running program in operating system. It consists of program code, data, and resource required and execution. And a process can both program and execution. It represents a single instance of program running on computer system. When a program is loaded into a memory and executed, it becomes a process. Each process has its own memory space, resource, and state. Process can perform various tasks such as executing instructor, accessing files, communicating with other processor, and interacting with user. So, in summary, a process is a fundamental concept in operating system that encapsulates the execution of a program and represent an active unit of work within a system. After knowing about the process, we will talk about the process states in CPU schedulers. In studying operating system, understanding process and their management is crucial. A process can count an instance of program and execution. It encompasses various stages from creation to termination, each within its own significance. Initially, a program resides in storage, awaiting execution. When triggered, it moves into a memory and is referred as a process. This transition marks the program's activate state. For instance, when user clicks an application icon, the accession program transformation into a process, initiating an execution. Its execution. A process consists on different components such as code section, data section, stack, and heap. This segment hold distance information vital into our execution of the process. For example, the code section contains the program instruction, while the data section stores global variables. A process undergoes states transition during its life cycle. The states include first about a new. This state indicates that process has been created but has not yet started execution. The second is ready. In this state, the process ready to execute but awaits allocation of CPU resource. The third is running. The process is actively being executed by the CPU, performing its design task. The fourth is waiting. When a process needs to wait for an event to occur, such as input, output, operation, it enters this state. The fourth, the fifth is terminate. Upon, upon completion of its task, the process is terminated, freeing up system resources. Consider the example of a web browser program. When it launched, it spawned multiple processes for tasks like rendering web page, handling user input, and managing network requests. Each of these processes transition through the aforementioned states as it executes. The operating system employ a scheduler to manage process efficiently. The scheduler determines which process to execute next based on various factors like priority, resource availability, and the schedule algorithm. For instance, in a multi-user environment, the scheduler prioritizes critical tasks to ensure smooth operation. If a high priority process arrives while another is running, the scheduler may preempt the current process, placing in the back in the ready queue and execute the higher priority one. In essence, understanding process management is integral to comprehending the function of operation system. Process undergo dynamic transition is contributing to the overall efficiency and responsiveness of system. Through, through effective scheduling and resource allocation, the operating system orchestrates this process, ensuring optimal utilization of system resource and responsiveness to user interaction. Okay, so next we're going to talk about the process control block, the attribute of a process. It's explained with an example. So the process control block or PCB, also known as task control block, is crucial data structure in operating system that contains various attributes and information associated with the process. Okay, let's explore the attribute of a PCB with the example. First, about a process status. This attribute represents the current state of process, such new, ready, running, waiting, or terminate. For example, a process P1 may be in a running state while another process P2 is in waiting state, waiting for input or output operation to complete. The second is about process number or ID. Each process is assigned a unique identifier known as process ID. This helps in identifying and managing process. For instance, a process with ID 1001 may correspond to a web server process. The third is about program counter, PC. The program counter stores the address to the next instruction to be executed by the CPU for that process. For example, if a process is executing a loop, the program counter will point to the next instruction inside the loop. The fourth is register. Register store the current state of the CPU for a particular process. This includes data register, address register, status register. For instance, the accumulator register may hold intermediate resulting during arithmetic operation. The fifth is about memory limit. This attribute specific that memory boundaries allocate to the process. It indicates the start and end address of memory region allocate to the process. For example, a process may be allocate memory for address 0 x1000 to 0 x1 x2000. The sixth is about list of open files. Process often interact with files on the system. The PCB maintains a list of files opened by the process, along with their file description. For instance, a process may have files like input.txt and output.txt open for reading and writing. The seventh is about accounting information. This includes details such as CPU usage, execution time, and resource allocation. For example, the PCB may be record that a process has used 80% of the CPU in the last hour. The eighth is about memory management information. This attribute includes information about the process memory requirement and memory allocation. It specifies how much memory the process needs and where it allocated in the memory hierarchy. The PCB play a crucial role in process scheduling and context switching. It stores all the necessary information required to manage and control the execution of process efficiently. When the CPU switches from one process to another, it saves the state of the current process in its PCB and loads the states of the next process to be executed. In summary, the PCB is the vital data structure in operating system that encapsulates all essentially information about process, facilitating efficient management and execution of process in system. And after that, we will talk about process scheduling. eh, Specifically about the threads versus the process. In operating system, understanding the concept of the threats, and process is crucial, especially in terms of process scheduling and managing system resources efficiently. A process can be thought of as an heavyweight task, while the thread is a lightweight unit within a process. Just like in real life, where a task may involve multiple smaller activity, a process can encompass various threads to handle different aspects of task. For example, in Microsoft New Word, process handle tasks like spell checking, grammar checking, and formatting, which are implemented as threads within a process. Operating systems employ multi-programming and time-sharing techniques to maximize CPU utilization. Multi-programming ensures that CPU always has a sound process to execute, reducing idle time. Time-sharing systems allow multiple processes to appear as if they are running simultaneously by quickly switching between them. The process scheduler plays a vital role in deciding which process get access to the CPU next. It maintains various scheduling queues, such as the jobs queue containing all process, that already queue containing process ready to execute, and device queue containing process waiting for input or output operation. In a single processor system, only one process runs at a time, but the CPU switches between processes so rapidly that it appears as if they are running concurrently. The process scheduler selects the next process based on predefined criteria such as priority or completion time. Process may transition through different states such as new, ready, running, waiting, and terminate. The scheduler handles this transition, ensuring that process progress smoothly through their life cycle. Overall, understanding threads, process, and process scheduling is essential for efficient resource management and system performance in operating systems. Okay, next we will talk about the scheduler type. It's about a long-term or short-term or medium-term scheduler. In operating system, there are different types of scheduler that handle various aspects of process management. So let's delve into a basic of long-term, short-term, and medium-term scheduler. The first is about short-term schedulers or CPU scheduler. The short-term scheduler, also known as a CPU scheduler, is responsible for selecting which process to execute next and allocating the CPU that process. It works by selecting process from the ready queue and dispatching them into the CPU for execution. The short-term scheduler operates at the fast pace, typically within a milliseconds and in invoked frequently to ensure efficient CPU utilization. For example, when the multiple processes are waiting in ready queue, the short-term scheduler decides which process to execute next based on a criteria like process priority, CPU press time, or scheduling algorithm. So the second we will talk about the long-term scheduler or job scheduler. A long-term scheduler, also called the job scheduler, manages the admission of new process into the system. Its main task is to select process from the pool of incoming jobs typically residing on the disk and load them into a memory for execution. The long-term scheduler controls the degree of multiprogramming by determining how many processes should be resident in memory at given time. Unlike the short-term scheduler, a long-term scheduler is invoked infrequently and operates at a slower pace, often in seconds or minutes. For example, when a new process is initiated or arrives in the system, the long-term scheduler decides whether to admit it into a memory based on factors like memory availability, system load, and process priority. The third is about medium-term scheduler. The medium-term scheduler is a relatively New Year addition to the scheduling hierarchy in some operating system. Its primary function is to manage the process memory utilization by deciding when to swap process between memory and disk. When a process is removed from memory, like due to lack memory space or to improve overall system performance, the medium-term schedulers handle the swapping process. It removes process from memory and places them on disk, freeing up memory resources for other processes. The medium-term scheduler helps maintain a balance between memory utilization and system responsiveness. For example, when a process memory has been idle for a long time or needs to be suspended to prioritize other process, the medium-term scheduler decides to swap it out memory and onto disk. Okay, so next we will talk about the CPU bound versus input. Output bound process, CPU scheduling, basic of the operating system. In CPU scheduling, the process can be categorized based on their utilization of CPU and input or output operation. So let's discuss the difference between CPU bound and input or output bound process. The first is about CPU bound process. CPU bound process are those primarily require CPU resource for their execution. This process spend most of their time performing computation, calculation, or their CPU-intensive task. They require minimal interaction with input or output device and spend the majority of their time executing instructions on the CPU. Example of CPU-bound process include mathematical computation, simulation, and scientific calculation. CPU-bound process typically have long CPU burst times, meaning they require extended periods of the time on CPU without needing to perform input-output operation. Input or the second is about input or output process. Input or output bound process are those that primarily require input or output resources for their execution. This process spend most of their time waiting for input or output operation to complete, such as reading from or writing to disk, network communication, or user interaction. They perform relatively fewer computation on the CPU compared to input or output operation. Example of input-output burn process include file input-output operation, network communication, and user interface interaction. Input or output burn process typically have short CPU burst times as they spend a significant portion of their execution time waiting for input-output operation to complete. In summary, CPU-bound process heavily utilize the CPU for computational tasks and have long CPU burst times, while input or output-bound process rarely rely more on input or output operation and have shorter CPU burst times due to frequent waiting for input or output operation to complete. An efficient CPU scheduling algorithm should take into account the characteristic of both CPU bound and input or output bound process to optimize system performance and resource utilization. Okay, next we will talk about the CPU scheduling. It's about the preventive versus a non-preventive CPU scheduling algorithm in operating system. In CPU scheduling algorithm, there are two major approaches, preemptive and non-preemptive. let's discuss each approach in detail. The first is none. In non-preventive scheduling, once a process starts executing on CPU, it will continue to run until it completes its CPU press voluntarily or blocks for input or output. Processor allocate the CPU for their entire execution time without interruption. If a higher priority process becomes ready to run while a lower priority process is currently running, the lower priority process will continue until it finishes, and it only then will the higher priority process be scheduled. Non-preventive, non-preemptive scheduling algorithm include first come, first served, or FCFS, shortest job next, SGN, and priority scheduling. These algorithms are simpler to implement but may result in poor system responsiveness, especially if long-running process block in CPU for extended period. The second is about preemptive approach. In preemptive scheduling, a running process can be first safely removed from the CPU before it completes its CPU burst. The CPU scheduler may interrupt the execution of a running process and allocate the CPU to another process by uncertain condition or priorities. The preemptive schedules allows to better responsiveness and higher system utilization compared to non-preemptive scheduling. Common preemptive scheduling algorithm round robin shortest remaining time first SRTF and priorities preemptive scheduling. The preemptive scheduling algorithms are more complex to implement but can be lead to the better system performance, especially multitasking environment where multiple processes complete for the CPU time. So the preemptive scheduling allows a process to run to completion without interrupt, while the preemptive scheduling allows CPU scheduler to interrupt running process to allocate to the CPU to higher priority task. The choice between preemptive and non-preemptive scheduling depends on system requirement, including responsiveness, system overhead, and fairness. Okay, next is about the process termination. In the chapter on process management in operating system, we are now discussing process termination. When does a process get terminated and how does it happen? Let's delve into the details. First is about the normal termination. A process is terminated when it reach its statement and complete its execution. The operating system is notified of the completion through a system call, typically called exit. Upon termination, the process may return a status value, typically indicating its completion status to its parent process. Resources allocated to this process, such as memory and open files, are released by the operating system. Termination by parent process. It's about the second thing that we will talk about. The parent process may choose to terminate its child processing using a system call such an abort. So this can happen if the parent process no longer needs the child functionally or resources. The parent process can wait the termination of its child process using the wait system. The third is about the automatic termination by operating system. If a parent process terminates before its child process, some operating system automatically terminates all child process. This ensures that no child process exits without a parent and help maintain system integrity. The fourth is about the orphan process. An urban process is one whose parent process terminates before it does. In such case, the urban process is assigned a new parent, often the unit product process, which ensures its continued execution. Urban process can also be terminated automatically by the operating system if they remain without a parent for too long. And the five is about the zombie process. So what is zombie process? Zombie process is one that has complete execution but still has an entire in the process table. This can happen if the parent process does not invoke the wait system call to retrieve the termination status if of this child process. Swimming process management system resources and should be avoided by properly handling process termination in the parent process. In summary, process termination involves the completion process execution, release of allocate resource, and paper handling by the parent process or their operating system to ensure system stability and resource efficiently. Understanding process termination is essential for effective process management in operating system. Okay, next is about the operation and process. I is about the process creation. In the chapter of process management in operating system, we are discuss operation and process. The details is the first is about the process creation. The system must provide mechanism for creating process. Operation performed on process include process creation and termination. A parent process can create several new processes during its execution using system calls. Each process created becomes a child process of the parent process, forming a hierarchy. A child process can further create their own children, leading to a tree-like structure of process. The processes are identified by unique process identifiers, or pipes, and the process sharing between parent and child process can be managed in various ways. All resources can be shared between parents and children. Children can share the most top parent resources. Parents can and children can share no resources. And when the parents create a child process, it can either execute concurrently with the parents or wait for the child to terminate. The child process can inherit a duplicate of parents' address space and execute data or start with its own independent execution. And process creation is initiated by system calls. The fork system call is commonly used to create new process. After create child process, a parent process may replace its memory space with a new program using a system call. The parent process typically waits for the child process to complete its execution before proceeding further. An example code as in the C programming language demonstrate process creation, identification, and execution. So, the process creation involves the creation of new process by parent process, forming a hierarchical structure. Various system calls are used to manage the creation, identification, and execution of process, ensuring efficient resource utilization and task execution in operating system. Okay, next is about the context switching multitasking concept. Into the lecture, we will discuss the concept of multitasking and context switching in operating system. The first is about multitasking on mobile system. Early version of mobile system allowed only one process to run at a time. User interface process were given priority while background process were suspended. The background process includes like receiving notification, specific long running tasks, and audio playback. And nowadays, mobile systems support multitasking, allowing multiple applications to run simultaneously. The background process can continue running in the background without a user interface. Such as task scheduling and memory management enable efficient multitasking on mobile device. This second, we'll talk about the context switching. Context switching is a mechanism by which the operating system switches between processes. When multitasking, the CPU moves from executing one process to another, switching their execution context. The state of the old process, including its program counter, register, and other relevant information, saves in data structure called the process control flow or PCB. The state of the new process is then loaded from the PCB, allowing to resume execution, and the context occurs at such a rapid pace that user perspective multiple process running simultaneously. Need for context switching arises from the time-sharing nature of operating system, where the CPU time is allocated to multiple processes. It allows operating system to efficiently manage CPU resources and ensure fair execution of process. Context switching involves some overhead as system resources are temporarily idle during the switching process. The complexity of context switching depending on the complexity of the operating system and the hardware architecture. The advanced hardware features such as multiple register can speed up context switching by allowing multiple switches to occur simultaneously. In conclusion, multitasking and context switching are essential concepts in operating system, enabling efficient resource utilization and seamless execution of multiple processes. They play a crucial role in providing a responsive and interactive user experience on modern computer devices. About the inter-process communication, I want to tell you, I want to ask you guys, who guys ever experienced the back partner phase? Oh my god, it's really hit me hard. So, let's playing a back partner Nikki 1 hour loop. While I explain about the inter-process communication. In today's lecture, we delve into the concept of inter-process communication (IPC) in the context of process management in operating system. The first is type process. Within a system, there are two types of process: independent and cooperative. Independent process do not affect other process and are not affected by them, and cooperative process in other hand, can affect and be affected by other process. Second is about need for interprocess communication or IPC. IPC facility communication between cooperative process. It allows process to share data, programs, and resources among themselves. IPC mechanism enable process to work together efficiently within system. And about the IPC mechanism, IPC involves two main mechanisms, shared memory and passing. The shared memory model process share a common region of memory to exchange data and communicate. And passaging model process communication by sending message to each other, facilitated by operating system kernel. And we will battling about the shared memory and message passing. The shared memory model is provide fast communication but requires synchronization mechanism to avoid conflict. The message passing model ensures isolation between processes but may incur overhead due to system calls for message passing. An advantage of cooperative process and IPC is about the information sharing. Cooperative process can share data and information in sharing collaboration and complex competition and speed, dividing tasks into multiple processes allow for parallel execution, speeding up overall performance. Modularity process can be divided into smaller modules for easier management and development. Resource utilization IBC enables efficient sharing of system resource among where process optimizing resource usage. So, for conclusion, APC plays a crucial role in enabling collaboration and communication between process within an operating system by facilitating data and sharing and resource utilization. APC mechanism in change by efficiently and performance of cooperative process. In the next lecture, we will explore the share memory and message passing model of IPC in more detail. So, guys, I was asking him about, uh, um, are you live because I look alike with your ex, and he said yes. I don't know how to react, and I block him in every social media because of it. Oh my god, that bastard! You know this lyric about it. But I know in a week or so you'll fade away. You can, now it's there. I can. You're still there. Because, oh my god, I'm really sad right now. But I should finish this lecture. Okay, let's finish. Okay. But first thing first, I want to apologize about what I said before. I was cursing him here. I know that's bad, but I can't remove it because I already tired and I don't want to uh, re-explain. So I think I will just put that into the explanation and won't take another video game because it is tiring. Okay, next about the producer and consumer program in operating system. Uh, We focus in part to producer and consumer program, which is a classic synchronization problem in operating system. So here is a summary of the key points are covered. Sorry for the okay, let's skip it. First, about introduction to producer-consumer problem. The producer-consumer problem involves two processes, the producer and the consumer. The producer generates data or item while the consumer consume or process them, and the concurrency in producer and consumer process. Both the producer and the consumer process run concurrently, meaning they execute simultaneously to ensure smooth execution. It's crucial to have mechanism for sharing data between them. Next about the buffering and shared memory. A shared memory region, often referred to a buffer, serves as the intermediary between the procedure and the producer and consumer. The producer stores item in the buffer, and the consumer retrieves them from the buffer for processing. The buffer helps decouple the producer and consumer, allowing them to work at their own pace. The third is about synchronization between producer and consumer. Synchronization between the producer and consumer is essential to prevent issues such as data inconsistently or buffer overflow. One approach to synchronization is to ensure that the consumer waits the produce to produce an item before attempting to consume it. This synchronization ensures that the consumer does not consume items that have not yet been produced, avoiding a potential error. The five is about types of buffer. Buffers can be categorized into two types: unbounded buffer and bounded buffer. Unbounded buffer have no predefined size limit, allowing the producer to continue producing indefinitely. Buffers have a fixed size limit, which may lead to blocking if the buffer becomes full. The sixth is about the solution strategies. Various strategies such as using semaphore or mutex locks can be employed to implement synchronization between a producer and the consumer. These strategies can ensure that data is shared safely and efficiently between the producer and the consumer process. Illustrative example. An example scenario with bound buffer size 12 was provided, demonstrating how the producer and consumer interact with the shared buffer. The producer generates an item to the buffer, while the consumer retrieves item from the buffer for processing. In the lecture, we will delve deeper into implementation details of synchronization mechanism and explore additional strategies for addressing the producer-consumer program efficiently. Okay, stay tuned for further insight into process management and synchronization in operating system. If I'm not get tired. Okay, this is the last chapter about the shared memory. I don't know, like it takes 2 hours just to record this, so if you guys hear this section, I just want to say thank you because I know that my English is really bad, but you guys still keep watching this. I love you guys. And about the person that make me in a back partner face, I hope he die as soon as possible. Kesel banget gue. Oke lanjut. About a shared memory. In today's lecture, we delved into a topic in the process of communication, our IPC operating system, focusing specifically on shared memory as a mechanism for communication between process. Here's a breakdown of a key point covered. First, about introduction to shared memory. The shared memory is area that is shared among multiple processes for communication purpose. It serves a buffer or region where process can exchange data with each other. The second is characteristic of shared memory communication. Shared memory communication occurs directly between user process without direct intervention or control by the operating system kernel, unlike other forms of IPC, such as message passing, shared memory communication allow process to interact more freely and efficiently. The third is about the advantage of shared memory. Shared memory communication offers low overhead and high efficiently since it involves direct memory access by user process. It allows for fast and flexible communication between process, making it suitable for various applications and scenarios. The fourth is about challenge and consideration. One challenge of shared memory communication is ensure proper synchronization between processes to avoid conflict and data consistently. process must coordinate access to shared memory to prevent issues such as race condition or data corruption. The synchronization mechanisms such as semaphore or multi clocks are used to coordinate access to shared memory among processes. This mechanism ensures the process access shared memory in a controlled and synchronization manner, preventing conflict and ensure data integrity. And the shared memory communication might require process to agree on access restriction and data and synchronization measure to prevent conflict. Process must follow agreed protocol for accessing shared memory to maintain consistently and avoid data loss corruption. Further discussion of said synchronization mechanism and technique will be covered in detail in Chapter 5 of the course. Topics such as mapper, multi-clocks, and other synchronization primitives will be explored to provide a comprehensive understanding of synchronization in shared memory communication. So, in conclusion, shared memory communication offers a powerful and efficient mechanism for inter-process communication in operating system. By carefully managing access and synchronization, process can effectively exchange data and collaborate without direct intervention from the operating system kernel. So stay tuned for more insight and discuss synchronization technique and shared memory communication in the future lecture if I'm not get tired. In conclusion, again, I don't know how much I say in conclusion in this video. I really sorry, but it was udah maaf gitu intinya. Understanding process management in operating system is paramount for grasping the make of modern computing environment by delving into life cycle of process, the intricacies of scheduling algorithms, and the mechanism of inter-process communication, we gain insight into how operating systems efficiently orchestrate the execution of tasks optimizing resource utilization, and ensure seamless user experience. As we navigate the complexities of process management, let us remain inspired by the endless possibilities it unlocks and commit to harnessing its power to drive innovation and advancements in ever evolving landscape of technology. So, thank you for joining me in this learning journey through process management in operating system. Bye bye.